Welcome viewers. Today's topic is inner product, but before I start inner product, I like to give an example on the theory which we have developed in the last lecture regarding change of basis. We have developed some results like Vs is equal to Pts Vt, but we could not we could not take up examples to illustrate this result. Today I will start with this example first, illustrate this, and then I will go to the inner products. Now to start with, let us say V is a vector space of dimension n, S and T be its two subspaces, S consisting of V1, V2, Vn is the basis for S, and T is W1, W2, Wn basis for V. Now let us say the vector V can be expressed as Vs in terms of the vectors V1, V2, Vn and Vt in terms of basis W1, W2, Wn. Then the relationship between Vs and Vt, this we have derived in my last lecture as Vs is equal to Pst, a matrix, multiplied by column vector Vt. This matrix is called transition matrix, and it is called transition matrix from T to S. Now to illustrate this, we have to find out Aij. What is Aij? Aij is a typical element of this matrix. Now to get Aij, we have to solve n systems of order n by n. So let me illustrate this with an example. So let us consider S a subspace of R2 consisting of bases 1, 2 and 0, 1, and another basis T 1, 1, 2, 3. These are two bases for R2. We have to find the coordinates of vector V, which is 1, 3 and 5, 4 with respect to basis T. This is first part. In the second part, we have to find the transition matrix Pst from T to S to the basis S. Now in the first part, you have to find the coordinates of V with respect to T. Now this can be obtained from the solution of the system, which is obtained as 1, 3 is equal to A 1, 1 plus B 2, 3. That means I want to express this vector 1, 3 as a linear combination of basis vectors 1, 1 and 2, 3 of the basis T. Now to this, to get A and B, I have to solve this system, and the system is A plus 2B is equal to 1, which is coming from the left hand side, and A plus 3B is equal to 3 from the right hand side. When we solve this equation, you can very easily solve it, subtract this from this, that will give me B is equal to 2, and substituting B is equal to 2 in one of these equations, we get A is equal to minus 3. So 1, 3 can be expressed as a linear combination of two vectors, or we can say the representation of 1, 3 in the basis T is 2, minus 3. Similarly, the vector 5, 4 is represented as a linear combination of basis vectors of T, A 1, 1 plus B 2, 3, and we again solve this system of equations to get B is equal to minus 1 and A is equal to 7, and that means 1, 3 in T basis representation is minus 3, 2, 5, 4 is 7 minus 1 in the basis T. Now the second part is to compute the transition matrix, you have to represent the vectors of T basis in S basis. That means first we consider the vector of S basis 1, 1, we write down it as A 1, 2 plus B 0, 1, and we solve it as we have done in the earlier part. So A is equal to 1 and B is equal to minus 1 is the solution of this. Then the second part, 2 comma 3, this is the second vector in the basis. So we express it again as a linear combination of 1 2 and 0 1, and we form a system of equations as this. They are solved to get a is equal to 2 and b is equal to minus 1. Solving this, we write down the transition matrix. The first vector is written as the column of this transition matrix. This is W1, and this is the second vector corresponding to 2 comma 3. So this is the transition matrix. Now let us try to verify the result which we have developed, that is Vs is equal to Pst Vt. For this we say 1 comma 3s is equal to 1 comma 1. This can be obtained by solving as we have done here, and then we say 1 comma 1, this is Vs, is the transition matrix which we have obtained here, multiplied by Vt. Vt is the vector 1 3 in T. This we have already obtained as minus 3 2, and if you really perform this multiplication, you can see that 1 comma 1 multiplied by minus 3 plus 2 into 2 is 1, and this one is equal to minus 1 into minus 3 minus 2, that comes out to be 1. So the result is verified. Now with this we have completed the example, and now we go to the inner product. So the contents of this lecture consists of the definition of inner product, the inner product spaces, norm, distances, orthogonal vectors, orthonormal vectors, Gram-Schmidt process. To define inner product, let us consider V be any real vector space. An inner product on V is a function from V cross V to R. That means a real number is assigned to each ordered pair UV of vectors denoted by U comma V. So this is the notation we use for inner product of U and V, provided it satisfies the following properties. The first property, we call it as positive definiteness. This means that V comma V, the inner product of V comma V, is greater than equal to 0, and V comma V is 0 if and only if V is a 0 vector in V. So V comma V is 0 only when V comma V is 0, when V is a 0 vector. This is the positive definiteness. And the second is the symmetric property. This means that inner product of U and V is the same as inner product of V and U for all pairs of U and V in V. The second property. According to third property, U plus V comma W, their inner product is equal to inner product of U and W plus inner product of V and W for all U, V and W in V. And the last one, Cu comma V, inner product of Cu and V is equal to C times inner product of U comma V for all U, V and V, and C being a real scalar. So if it satisfies these properties, then an inner product is defined. On the basis of these four properties, the following properties can easily be derived, that is U comma CV is equal to C times inner product of U comma V, because it is symmetric. So CV comma U is the same as U comma CV, and then C can be taken out. So U comma CV is equal to C times U comma V. And the third one, the next property which can easily be derived is U comma V plus W is equal to U comma V plus U comma W, and again it is derived from the symmetric property, and then using the third property one can easily arrive at this result. Let us take an example. So if we have a vector U in Rn as U1, U2, Un and V as V1, V2, Vn, then if we define U comma V as U1, V1 plus U2, V2 plus Un, Vn, then it defines a vector and it defines an inner product. It defines an inner product means we have to verify that it satisfies all the 4 properties which we have described just now. So, to start with u comma u, u comma u is u1 square plus u2 square plus un square, because we are taking u at both the places. So, this is the inner product according to this definition, and this is a square of real numbers, sum of squares of real number, it is always be positive, and this is 0 only when u1 square plus u2 square plus un square is equal to 0. Since all these numbers are positive, so their sum will be 0 only when individual terms are 0, u1, u2, un is 0. That means u comma u is 0 simply means that u is 0. So, that is the first part, and if u is equal to 0, then u1 square plus u2 square plus un square is equal to 0. So, u comma u is 0 for 0 vector. That proves the first part. The second part is that u comma v and v comma u are same. So, according to the definition, u comma v is u1 v1 plus u2 v2 plus un vn, and since u1 and v1 are real numbers, so they can be commuted. So, u1 v1 can be written as v1 u1, similarly the next term v2 u2, and the last term un vn is expressed as vn un, and again applying the definition we can see that this is nothing but v comma u, and that means the symmetric property is also proved. Now, the third property, u plus v comma w. So, if we consider u plus v as u1 plus v1, u2 plus v2, un plus vn, and w as w1, w2, wn, then by applying the definition of inner product, it is u1 plus v1 multiplied by w1 plus u2 plus v2 multiplied by w2, and so on, and the last term will be un plus vn multiplied by wn. And since these are nothing but simply real numbers, so u1 plus v1 multiplied by w1 is nothing but u1 w1 plus v1 w1, and u2 v2 multiplied by w2 is u2 w2, and here we are writing v2 w2, and so on. This is possible because these numbers are real numbers, and we have collected terms first for u1 w1 and second for v1 w1, etc. And that means u plus v comma w, this inner product is equal to inner product of u w plus inner product of v w, and that proves the third property. The fourth property is cu comma v. So, we consider the right hand side by applying the definition cu1 v1 plus cu2 v2 plus cun vn. C can be taken outside. So, what we have is u1 v1 plus u2 v2 plus un vn, and this is nothing but C times the inner product of u comma v, and that proves the last property, and this means the definition which we have given, that is the definition of an inner product. Now, the inner product defined in this example is called the standard inner product, and if we realize, then this inner product is the dot product of vectors. So, inner product is a generalization of dot product for vectors. This is what we like to conclude, and then inner product is actually a generalization of dot product, and in fact it can be defined in many different ways. So, in this example we say that this definition u comma v is equal to u1 plus v1 plus twice u2 v2 plus thrice u3 v3 also defines an inner product. So, the same way as we have done for the earlier definition, we apply this. So, we again check the first property, u comma u is equal to, according to second definition, it is u1 square, u1 and v1 they are equal, so u1 square. The second term is twice u2 v2, u2 and v2 are equal, so it is twice u2 square the second term, and third term is 3 u3 v3, since u3 and v3 are equal, here we have u comma u, so it is thrice u3 square, and again this is greater than equal to 0, and u comma u is 0 implies that u1 is equal to u2 is equal to u3 is equal to 0, because all these terms are positive terms. They can be 0 when individually each of them is 0, and that means u comma u is 0 only when u is equal to 0. And of course, if u is equal to 0, that means u1, u2, u3 are 0, then u comma u, the inner product u comma u is also 0. So, that proves the first property for this definition. Now comes the second property, u comma v is equal to u1 v1 plus twice u2 v2 plus 3 u3 v3 according to the definition. Then we can again commute individual terms being real numbers. So, we can have v1 u1 plus twice v2 u2 plus thrice v3 u3, and this simply means that u comma v inner product is equal to inner product of v comma u, and that proves the symmetric property. Third is u plus v comma w is equal to u1 plus v1 w1 plus 2 times u second component u2 plus v2 multiplied by w2 plus 3 times the third component u3 plus v3 into w3, or we can write it as u1 w1 plus twice u2 w2 plus thrice u3 w3 is plus v1 w1 plus twice v2 w2 plus thrice v3 w3. That means we are reorganizing terms in this particular manner, and then we can easily see that u plus v comma w is equal to inner product of u comma w plus inner product of v comma w. That proves the third property. And the fourth is C u comma w is equal to C u1 w1 plus twice C u2 second term multiplied by w2 plus thrice C u3 multiplied by w3, and then C can be taken out from each of these, and that proves the final result C u comma w is equal to C times the inner product of u comma w, and that establishes that the definition which is given to us is a definition for inner product. So, we can for R3 we can have two types of inner product defined. One, the way we have the standard inner product which we have defined in another earlier example, n is equal to 3, and this is another definition for inner product. So, for a vector space we can define inner product in many different ways. So, more than one inner product can be defined on a given vector space. And this is the remark which can be obtained from this example. Now, we define inner product space. So, we say a real vector space V with an inner product is called an inner product space. So, to define an inner product space, what we need is we have to define an inner product on a real vector space. Normally, R n with standard inner product is called as Euclidean n space. Now, few more definitions. Suppose V is an inner product space, then the norm or length of vector u is denoted by this symbol and is defined as, we call it as norm of u as under root of inner product u comma u. This is one definition, and the another definition is for the distance between two vectors u and v, and it is denoted by d u comma v, and is defined as d u comma v is equal to norm of u minus v. Now, let us illustrate this with example. So, compute lengths and distance between given vectors u 1 comma 1 comma 1 and v as 4 0 3 with the standard inner product on R3 and weighted inner product defined as u comma v is equal to u1 v1 plus twice u2 v2 plus thrice u3 v3. So, we solve it. We start with standard inner product on R3. So, first we have to find the length. So, length of the vector u which is 1 comma 1 comma 1, it is defined as under root of inner product of u comma u, the standard inner product of u comma u. It is 1 plus 1 plus 1. So, it comes out to be under root 3, while for v, while for the other vector 4 0 3, it is 16 plus 9, it is coming out to be 5. So, this is the length of 4, 0, 3. The distance u comma v is norm of u minus v, and if given u and v, it comes out to be norm of 3 comma 1, 3 comma minus 1 comma 2, and its inner product will be 9 plus 1 plus 4, that comes out to be under root 14. So, distance between u and v on the standard inner product is under root 14, while if we consider the weighted inner product defined as this, then the norm of u is 1 plus 2 plus 3, and this comes out to be under root 6, while for the second vector it is 4 plus 3 comma 9, this is 3 and u3 square is 9. So, it is 4 plus 3 into 9, that comes out to be under root 31. So, norm of v on weighted inner product comes out to be under root 31. Now, the distance between u and v on this inner product, weighted inner product, is 3 norm of 3 minus 1 comma 2, and this comes out to be 3 u comma v is 3 into 3 plus 2 times minus 1 into minus 1, that is 1, plus 3 times u3 v3, that is 3 times 2 comma 2. So, it is 4, and this comes out to be under root 23. Now, we discuss some properties of norms and distances. So, suppose u, v and w are vectors in an inner product space and c is any scalar, then the following properties can be easily established. First property is u minus, the inner product of u minus v and w is u comma w minus v comma w. The second property is, previously we have addition here, now we have subtraction here. The second is u inner product of u comma 0 is the same as inner product of 0 comma u, and this is always 0. The third is inner norm of cu is equal to the magnitude of the scalar c multiplied by norm of u. Then norm of u is always greater than equal to 0. These are the properties which can easily be derived. And fifth is norm of u, if u is equal to 0 when u is equal to 0. Next is u plus v is less than norm of u plus v is less than equal to norm of u plus norm of v, and then we have duv is equal to dvu, that means distance between u and v or distance between u and v and u, it is the same. And eighth property is distance between u and v is less than equal to distance between u and w plus distance between w and v. This is called Schwarz inequality. Now, we discuss orthogonality of vectors. So, let us define it first. Let V be an inner product space. The vectors u and v in V are orthogonal if the inner product of u and v is 0. So, this is the definition for orthogonality of two vectors. Here the order of vectors is not important, because if u comma v is equal to 0, then inner product of v comma u is also 0 due to symmetry. So, if u is orthogonal to v, then v is also orthogonal to u. Now, a subset S of v is orthogonal if every pair of distinct vectors in S is orthogonal. Here we have defined orthogonality between two vectors. Now, we are defining orthogonality of a set of vectors. So, a subset S of v is orthogonal if every pair of distinct vectors in S is orthogonal. And then a vector v in V is a unit vector if the norm of this vector is 1. That is how we define unit vector. A subset S of V is orthogonal if S is orthogonal and V norm of V is equal to 1 for all vectors V in S. That means, if these two properties are satisfied for subset S, then this is called orthonormal. The first property is that S is orthogonal set and norm of each vector in S is 1. That is how we define orthonormal set. The set S consisting of u1, u2, un is said to be orthonormal if ui, uj is equal to sij, or we call it delta ij, if it is 0 when I is not equal to j and it is 1 for I is equal to j. So, this definition is actually means this. For example, if u1 and u2, I is equal to 1 and j is equal to 2. So, this is orthonormal if these two vectors are orthogonal. That means ui, u1 and u2, this is equal to 0 when I is not equal to j. This should be true for all I and j when they are not equal. But if they are equal, u1, the inner product of I comma ui when I and j are equal, that is norm, and this has to be 1 because it is an orthonormal vector. So, that is how we define orthonormal set, and mathematically we say that inner product of ui comma uj is equal to 0 for I is not equal to j and 1 for I is equal to j. So, if this property is satisfied for all I and j for a set S, then we say that set is orthonormal. If u and v are orthogonal, then u divided by norm of u and v divided by norm of v, these vectors will be orthonormal, because orthogonality does not mean orthonormality, because orthonormality wants that their norm should be 1, and so this additional property is required. So, if u and v are orthogonal, then to make it orthonormal you have to divide individual vectors by their norms. So, u and norm of u and v and norm of v will be orthonormal. So, this way we are actually getting the norm of the vectors as 1. If u and v are orthogonal, then cu and dv will also be orthogonal for scalars c and d. This can be easily proved, because if u and v is inner product of u and v is 0, then inner product of cu comma v is also 0 and inner product of cu comma dv will also be 0. So, this is what we have. Now, as an example, I have given a set of 3 vectors 1 0 minus 1, 0 1 0 and 1 0 1. We have to prove whether this, we have to find whether this is an orthogonal set of vectors or not. Now, to check this, we have to see whether they are orthogonal or not, whether this pair is orthogonal or not. So, let us consider 1 0 minus 1 and 0 1 comma 0. Let us form its inner product, and one can see that 1 comma 1 multiplied by 0, 0 multiplied by 1 minus 1 multiplied by 0 on the standard inner product, this is 0. If nothing is said, then we consider the standard inner product. So, we are considering standard inner product and this inner product is 0. Consider the second pair 0 1 0 and 1 0 1. Again, this is this set this pair is orthogonal, because 0 comma 0 multiplied by 1 plus 1 multiplied by 0 and 0 multiplied by 1 all are 0. So, it is this is also orthogonal, and there is third set 1 0 minus 1 and 1 0 1. If this is also, this pair is also set of orthogonal vectors, then we can say that this set is a set of orthogonal vectors. So, let us check this. 1 comma 1 is 1, this is 0, 1 comma minus 1 is minus 1. So, the sum is 0. So, this also is a orthogonal pair, and that means yes, the set S consists of orthogonal set of vectors. Now, let us see what are these vectors. The first vector 0 1 0, 0 1 0 is a vector on y axis. Then Another vector 1 0 minus 1, 1 0 minus 1 is this vector which is on y x plane, and this is on x z plane, x and z plane. The third vector is 1 0 1, this is also on x z plane, and so these two vectors, they are lying on x z plane, and this is third vector is y vector. So x z plane is y axis is perpendicular to x z plane. So these three vectors are orthogonal. Then these two vectors, whether they are perpendicular or not. So let us check whether they are perpendicular or not. So we have to compute the inner product. It is 1 0 1, 1 0 1 is this 45-degree line with this, and this is again on the negative side. So this is also 45. So that means this angle between these two vectors is 90 degree. So that is how these three vectors are orthogonal. So this is a geometrical interpretation. But these three vectors are orthogonal, but they are not orthonormal, although the norm of this vector is 1, but the norm of this vector is not 1. Similarly, the norm of this vector is not 1. So this set is not a set of orthonormal vectors, they are simply orthogonal vectors. The set S of vectors is called orthonormal basis for the vector space provided it satisfies two properties. One is it forms a basis for the vector space V, and the second is the set is orthonormal. Now see, we are defining a vector space, we are defining a basis for a vector space, but now we are interested in orthonormal basis for the vector space. So to have an orthonormal basis for a vector space, first thing is that it should form a basis for the vector space, and then it should have an additional property that the set is orthonormal. Now this is an example. You have to show that the standard basis E1, E2, E3 of R3 is an orthonormal basis. We have already seen that E1, E2, E3 forms a basis for the vector space. Now we have to show that these three vectors in the basis, they are actually orthonormal. So E1 is 1 0 comma 0, E2 is 1 0 1, and E3 is 0 0 1. So if you consider the product EI comma EJ, this is equal to delta IJ. You can check it for each pair. E2 E1 or E1 E2 is equal to 1 multiplied by 0 plus 0 multiplied by 1 plus 0 multiplied by 0, that is 0. Similarly, E3 comma E1 or the same as inner product of E1 and E3, this is also 0, and E3 inner product of E3 and E2 is the same as inner product of E2 and E3, this also comes out to be 1. And further, norm of E1 is inner product E1 comma E1 is 1 comma 1 multiplied by 1, that comes out to be 1. Similarly, norm of E2 is also 1, norm of E3 is equal to 1. So we have shown that E1, E2, E3 forms a basis, they are orthogonal pairs, they form orthogonal pairs, and then each vector is of magnitude or is of norm 1. So this basis is orthonormal basis. Now we have some more results on inner products. First result is that norm of U plus V square is equal to norm of U square plus norm of V square. Now to prove this, we consider U plus V square is U plus V comma U plus V. So we apply the property of inner products U plus V comma U plus U plus V comma V, and that means U plus V square is equal to, again we apply the same property here, U comma U plus V comma U. Here again we apply the same property U comma V plus V comma V, and that means this is nothing but norm of U square plus V comma U plus U comma V, and finally plus V square. And since U and V are orthogonal, this has been given to us. So, v comma u is 0 and u comma v is equal to 0, and that proves our result that norm of u plus v square is equal to norm of u square plus norm of v square. So, this result is proved. Now, we have an interesting result. It states that if S consisting of n vectors S v1, v2, vn, and since it is an orthogonal set of non-zero vectors, then v1, v2, vn are linearly independent. Now, this is an important result. So, let us see how we prove this. Suppose we have dependent relationship between v1, v2, vn, that means they are not independent. Let us say they are dependent vectors. Then there exists constant c1, c2, cn, not all 0, such that c1 v1 plus c2 v2 plus ck vk is equal to 0. There must be some k, not necessarily all n may be independent, but some k vectors may be linearly dependent. So, c1 v1 plus c2 v2 plus ck vk is equal to 0. So, we can say here that it is, if we take the inner product of this with respect to vi. So, I am taking inner product here. So, on the right hand side is inner product vi comma 0, this is 0. So, that is not a problem. So, we will take vi comma c1 v1 plus c2 v2 plus ck vk. So, this can be simplified as c1 into vi comma v1 plus c2 vi comma v2 plus ck vi comma vk is equal to 0. Now, this is the property of inner products, that is why we are taking c1 out, it is addition property and scalar multiplication property. Now, vi comma v1, this is 0. If I is not 1, it is going to be 0 because they are orthogonal. Similarly, this is going to be 0. So, all these will be going to 0. So, if I is not equal to j, vi and vj is, inner product of vi and vj is 0 due to orthogonality. That means, we have only ci multiplied by vi comma vi is 0 for all I is equal to 1, 2, 2, and whatever I you consider, this is going to happen, provided we know that vi comma vi is not 0. So, what we can say is ci vi, this is vi comma vi is vi square, norm of vi square, and this is not 0. So, that means ci is equal to 0, and this is a contradiction. We have said that there are non-zero ci's, that is why a dependent relationship is formed, but we have arrived at the contradiction. That simply means that the vectors are linearly independent. So, that proves the result. So, S is the set of independent vectors. So, if the set S consisting of orthogonal vectors, then this set is actually the set of independent vectors. So, this is an important result. Now, another result, suppose S is equal to v1, v2, vn is an orthogonal basis for inner product space V, then any vector v belonging to V can be expressed as this. Okay, so, let us try to prove this. There is one more result in this. Further, if S is an orthogonal set, then orthonormal set, then all this will be 0, all this will be 1. So, it is nothing but V is equal to V comma u1 into V1 plus inner product of V comma u2 multiplied by V2 plus inner product of V comma un multiplied by Vn. So, let us try to prove this. So, let us say V belongs to V. So, V is a vector belonging to V, and V1, V2, V3, Vn, they form a basis. So, V can be expressed as a linear combination of these vectors. So, V is equal to C1 V1 plus C2 V2 plus C3 V3 plus Cn Vn, and that means if we take inner product of this with respect to Vi on both the sides, then Vi comma V, inner product of Vi comma V is equal to C1 Vi comma V1, the first term, plus C2 times Vi comma V2, the second term, and the last term will be Cn and inner product of Vi comma Vn. Now, since S is an orthogonal basis, so Vi and Vj is equal to 0 and Vi comma V is equal to Ci multiplied by inner product of Vi comma Vi. Rest of the terms will be not contributing anything, only the ith term in which we are taking inner product of Vi with Vi, only that will be non-zero, that will multiplied by Ci, but rest of the terms will be 0. So, on the left hand side we have Vi comma V, on the right hand side we have only single term Ci multiplied by Vi comma Vi, but this is nothing but norm of this, norm of Vi, and that means Ci is equal to Vi inner product of Vi comma V divided by Vi square, and this can be done for all i's. So, with this we have done for Vi, but this can be done for V1, V2, Vn. So, this way we can find all Ci's, and that means our first result is proved. And of course, if S is orthonormal basis, then norm of Vi square is equal to 1 for all i's, and that is why we have the second result. So, this is another interesting result. Now, this is interesting because this result helps us in expressing the vector in terms of orthonormal basis. Now, we have another definition. Let V be a real inner product space. That means we have a vector space and an inner product is defined on it. Let W be a subspace of V. Then a vector U in V is orthogonal to W if U is orthogonal to all vectors in W. See, we were talking about orthogonality between pair of vectors. Now we are talking orthogonality of a vector with respect to a set of vectors. So, a vector U in V is orthogonal to W if the vector U is orthogonal to all vectors in W. That means inner product of W and U is 0 for every W in W. So, for this is true for all W's in this set W. If this is true, then we say the vector U is orthogonal to the set W. Then we talk about orthogonal complement of W is the set of all vectors in V which are orthogonal to all the vectors in W. We will come back to this again, and we say that orthogonal complement is denoted by W perpendicular. We will come back to this again. Now, let W be a subspace of inner product space V, then W perpendicular is a subspace of V, and W intersection of W perpendicular is 0. This is really an interesting result, that W intersection W perpendicular is 0. Now, to prove these results, let us say W1 and W2 belongs to W perpendicular and W belongs to W. Then W1 comma W is 0 and W2 comma W is equal to 0 because this belongs to W perpendicular. So, W perpendicular is a set of all vectors which are perpendicular to the vectors of W. So, that is the idea of W perpendicular. So, W1 plus W2 comma W, this will also be 0, and that means this also belongs to W perpendicular. Further, if W1 comma inner product of W1 comma W is equal to 0, that means C times W1 comma W, this inner product will also be 0. So, we have linear sum of two vectors belongs to W perpendicular, and sum with the and the scalar product will also belong to W perpendicular, and that means this is actually the definition of subspace. So, we say W perpendicular is a subspace of V. To prove the second property, let U belongs to both this W intersection W perpendicular, that means U belongs to W as well as U belongs to W perpendicular, and since U belongs to W as well as W perpendicular, So since the vectors of W and W perpendicular are orthogonal, so we take a vector from W and take a product, take a vector from W perpendicular, and then their inner product will be 0. So we take U from W and we take U from W perpendicular. So inner product of U comma U is 0, and that means when this happens, when U is equal to 0. So if U belongs to W intersection W perpendicular, then that vector has to be 0. So that simply means that W intersection W perpendicular is nothing but the 0 vector. Now we discuss Gram-Schmidt process for orthonormalization. Let us say a vector space V is given to us. It is a finite dimensional inner product space, and we have been given a basis S consisting of n vectors u1, u2, un. Then with the help of this process, we can obtain another basis v1, v2, vn for the inner product space V, which is orthogonal, and then from that orthogonal basis we can divide each vector with its norm, and we can have an orthonormal basis. So we will first describe this algorithm. So the step 1 is we consider any vector u1 from the set S, and let us call this vector as v1. In the second step, we consider another vector u2 from the set S and consider the span of these two vectors, and let us call that span as w1. Now we consider a vector v2 in the span w1 such that v2 is orthogonal to v1. So if we can get this, then v2 is a linear combination of c1 u1 plus c2 u2. u1 is nothing but v1, so we have this v2 is equal to c1 v1 plus c2 u2. Then we take the inner product with v1 and we try to check that v2 v1 comes out to be 0. So this equation is solved by equating it to 0, and this is what the geometric interpretation is. We have u1, we have u2 vector, they are not necessarily orthogonal, but from this linear combination of u1 and u2 we can find out a vector v2 which is orthogonal to u1. So this equation helps us in obtaining v2. So what we do is we solve this. C1 is equal to minus C2 inner product of u2 v1 divided by v1 square, and if we take C2 is equal to 1, then this vector v2 can be obtained as u2 minus inner product u2 v1 divided by v1 square into v1. So we have obtained vector v2 which is perpendicular to v1. So for given two vectors we have orthogonal two vectors. Now therefore the non-zero orthogonal vectors v1 and v2 are linearly independent. This we have just now proved. Now the span of v1 v2 is a subspace of W having dimension 2 because these vectors are independent. Further, span of u1 u2 is the same as span of v1 v2. Therefore the new basis v1 v2 will span the same subspace as spanned by v1 and v2. So we have got two vectors. Now we try to extend this to three vectors. For this similar procedure is applied. We consider span of three vectors u1 u2 u3 from the given set S, and we consider v3 in this, and we apply the same philosophy what we have done in earlier step. So v3 belongs to span of v1 v2 u3, and we choose v3 in such a manner that it is perpendicular to v1 and v2. So we have two equations. We have this equation v3 is equal to d1 v1 plus d2 v2 plus d3 u3, and we apply this concept, and this will give us u3 as v3 minus v3 u1 in inner product of this divided by u1 square multiplied by u1 minus inner product of v3 u2 divided by u2 square into u2. So one can obtain this equation with the help of this equation. So we got third vector. Similarly, v1 v2 v3 will be linearly independent orthogonal vectors, so that they form an orthogonal basis for span of u1 u2 u3. Similarly, we can apply more number of steps till we get all vectors vn, and to convert this basis to orthonormal basis, each vector ui will be divided by its norm. So this way we get the orthonormal basis, and the formula is first from u1 we will get v1, u2 after getting v1 we will apply this formula to get v2. This left hand side involves u2 and v1, then we will have V3. V3 is obtained in terms of V1, V2, U1, U2 and U3. So, this is known on the left hand side. So, from here we get V3 and we can go on applying this. This is the general expression for Vn, and then we can orthonormalize it. Then we illustrate this procedure with an example. So, we consider R3 instead of Rn, consisting of these 3 vectors 2 1 0, 1 0 1 and minus 1 1 as a basis for R3. We have to find an orthonormal basis using Gram-Schmidt process. So, what we have done is we first consider U1 as 2 1 0. So, U1 is 2 1 0. So, same is V1. The second step gives us this formula. So, we consider U2 as this vector 1 0 1. We can compute, we can substitute the values. U2 is 1 0 1, U2 comma V2 is 2 and V1 square comes out to be 5. We substitute the values here and what we get is V2, and V2 is obtained as this 1 0 1 minus 2 by 5, 2 1 0 is this vector. So, that is how we get V2, and the third step is this formula we have already obtained. We substitute the values U3 as minus 1 1, the third vector from the given set. We compute U3 comma V1 as minus V1. We compute U3 comma V2, which comes out to be 2 by 5, and then V2 square is computed as 6 by 5. These values are substituted here, and what we get is the vector V3, which is finally obtained as through series of expressions. We finally arrive at V3 as minus 2 by 3, 4 by 3 and 2 by 3. So, all the 3 vectors are obtained. Now, 2 1 0, 1 by 5, 1 minus 2 5 and 1 by 3 minus 2 4 2 form an orthogonal basis, and if you have to obtain the orthonormal basis, then we simply divide these vectors by their norms. So, this is 1 minus 2 5 is divided by under root 30 its norm, minus 2 4 comma 2 is divided by its norm. So, this is the orthonormal basis. One can check that this is orthogonal set and this is orthonormal set. So, that is how we apply Gram-Schmidt process to arrive at the orthonormal basis from the given basis. So, today viewer, at the end I will summarize what I have done today. I have given the definition for inner product. I have defined inner product spaces, their norm, distances. We have taken examples to illustrate this. We have discussed some properties of inner products. We have discussed orthogonal vectors, orthonormal vectors. At the end, we have discussed Gram-Schmidt process for orthonormalization, which I have illustrated with the help of examples. Thank you.